Good morning. So in today's lecture, I will continue my discussion on PEC water splitting for hydrogen production. If we just recollect what we have discussed so far, is that what is the importance of green energy, and then PEC water splitting, a process of producing hydrogen which is completely green, in that sense that there is no emission of carbon or carbon compounds. And then we have seen that what are the material characteristics required for PEC water splitting process. So what we have seen that we can have different choices of material as electrode in a PEC water splitting system. So one can have an N-type semiconductor as one electrode and a metal as counter electrode, or P-type semiconductor as photoelectrode and metal as counter electrode. One can also have N-type and P-type both as electrodes. Now, when we talk about PEC water splitting process, we remember that there are 4 important steps. First step is the generation of electron hole by photon or by sunlight, and then the transport of the charge carriers before they recombine, and third is the splitting of water with the energy that the charge carriers had been have now from the sunlight, whatever energy they have from the sunlight. With this energy they can split the water, and as we have discussed, the minimum energy which is required to split water is 1.23 electron volt, and that of course finally in one electrode we see production of hydrogen, and in other electrode we see production of oxygen. So production of hydrogen is known as hydrogen evolution reaction, and production of oxygen is known as oxygen evolution reaction. Now, what we have also seen that when we have this PEC water splitting system, we have actually an electrode which is photoelectrode, and then electrolyte, and then a counter electrode. So in between photoelectrode and counter electrode there is an electrolyte. So that means when we have this electrode, in the electrolyte there is an interface between electrolyte and the electrode, suppose the semiconductor electrode, N-type or P-type. And then we have seen then when such interface is formed, how energy band changes across the interface, and how the Fermi energy level of the semiconductor matches with the redox potential level, and then when we shine light on this system, a photovoltage is generated. This is what we have discussed in the previous class, and finally we address the benchmark issues of a PEC water splitting system. So if we have to take it to say production or for technology, it is important to know what are the benchmarks. So we have seen all the benchmarks that is required for a PEC water splitting system. We will come back to these benchmark points again when we will discuss individual PEC water splitting system. So let me again start with the 2 typical cases where we have one N-type electrode as photoelectrode and one P-type electrode as photoelectrode. So if we just look at this, so let me just draw a setup something like this. So let us draw a setup, PC setup, something like this. So we have the N-type electrode here and counter electrode here, generally it is platinum, okay, and then we have a circuit, so bias, okay. So in between we have electrolyte, this is conduction band, this is valence band, photon is falling here, okay. And then when we consider this as N-type electrode, we have a band bending like this. Okay. So this is the path of electron in this case, and this is the path of hole. Okay. So electron hole pairs are generated here. So now we have here OER, that means water to oxygen production, and here we have hydrogen production, H2O to hydrogen production. H2O to hydrogen production, or HER. Okay. So this is a case when we have N-type semiconductor as a photoelectrode. Now if I go to a P-type semiconductor, in case of P-type semiconductor, so this is again conduction band, this is valence band, and now this is P-type semiconductor. So photoelectrode is now the P-type semiconductor. So now electron will move in this direction and hole will move in this direction, okay. And then here we have H2O to hydrogen production, or HER reaction, and here we have H2O to oxygen production, okay. So all right, so these are two important configurations. One is N-type configuration, that means N-type semiconductor as the photoelectrode, and another is P-type configuration, or P-type semiconductor as photoelectrode. One can also see how this HER and OER reaction takes place when we have both photoelectrodes and counter electrodes as N-type or P-type semiconductors. Okay, so this means that when we consider a semiconductor as a photoelectrode, there are certain important properties which we have to consider for semiconductor. Some of these properties we have already discussed as an initial discussion of the photoelectrode material, and one important property which we discussed is their band gap. So as we know that the water splitting energy is typically 1.23 electron volt. Okay, so therefore the band gap of the semiconductor should be 1.23 electron volt or higher. Okay, so there is a range of band gap. It is typically it is seen that if it is around 2 electron volt, that is a good choice. Okay, and also what we have seen that the conduction band minima and valence band maxima of the semiconductor should be positioned in such a way that is straddle between hydrogen evolution reaction and oxygen evolution reaction. Okay. So now the question is when this process is going on, the photo complete the starting from this the shining by sunlight and then finally the hydrogen production. What is the time scale that is we talk about? So let us look at the time scale of different reaction that these are taking place. So I can divide these two as a photophysical process. Okay, suppose shining light, absorption of light, and then generation of charge carriers, and then another process which is photoelectrochemical process where we will discuss about production of hydrogen. Okay. So now after again discussing little bit of this introduction, let us look at again the electrode. Okay. So I discussed in the previous class the first the photoelectrode or n-type semiconductor electrode was introduced by Fujishima and Honda, and they use the material titanium dioxide. Okay, but we will see, or we have already discussed that titanium dioxide is having quite large band gap around 3.2 electron volt. So in such a large band gap, the problem is that there are a lot of transmission of light. Okay, so therefore one has to take care of these also. If there are a lot of photons getting transmitted, then we don't have much component of absorption, and therefore the efficiency will be less. However, titanium dioxide was used as we discussed previously because of its stability. So there are several factors which we have to look into when we discuss the material or the oxide material to begin with for as a semiconductor electrode. So what are the points? What are the criteria? So one is that this should be highly stable because the electrode is immersed in a solution, okay, and therefore it should not corrode the electrode or damage the electrode. So therefore the stability of the electrode should be very good, and then the material which are used in the electron should be earth abundant, because we always try to make the electrodes or the PEC setup as a whole as cost effective. That is important for technology, and therefore the material should be earth abundant. They should be easily available on earth. And third is environment friendly. This is always important because whatever material we use or whatever the component we use for any kind of the equipment or any kind of technology, we will always try to see the environment friendly material, and that is what we discussed in when we are discussing photovoltaics also. Some materials are toxic, some materials are environment friendly. Okay, so this is one important criteria which we have to always look for when we design a system or a material. Then fourth is tunable physicochemical properties. So tunable properties that what are the important properties that we have seen of a photoelectrode? Important property is its band gap. Okay. Important property is the absorption of light. Important property is the efficiency of transport of charge carriers inside the medium. Okay. And another important property is that it should be having less defect, and therefore the recombination should be less. So these properties should be tunable. So we can make the change or variation of these properties in the material. That is another criteria. And another is easy to synthesize. This is always important because when we talk about entire PEC setup, okay, we have a little bit of idea at this stage about the photoelectrochemical setup. I will discuss about the PEC setup again in detail in the next lecture. Okay, but whatever idea we have one photoelectrode, one counter electrode, and electrolyte. Okay, so it is important that when we, the grow this material, or photoelectrode material or counter electrode material, the synthesis process should be simple. Okay, so that we do not have much, the involved method in making these electrodes. And then exceptional ability to generate charge carriers under light irradiation. Okay, so this is what is extremely important point, because whenever we have this irradiation with light, they should, they generate the charge carriers and the process should continue. So when we talk about various materials as photoelectrode, we keep all these points in mind. And it seems that the oxide semiconductors are very good, candidates or potential candidates as photoelectrode. Although there are many other materials also, other compounds also, but oxides are so far seems to be very good, material or potential material for PC electrode. So if you just look at whatever people have reported in the literature, that if we plot the band gap along x-axis, so you can see the band gap is plotted along x-axis, and maximum conversion efficiency. So this is band gap along x-axis and this is maximum conversion efficiency. Okay, so generally the efficiency which is used for PC water splitting is called solar to hydrogen efficiency. Okay, STH efficiency. So how much power you give and how much hydrogen is being produced. So this is a kind of conversion efficiency. So if you look at, so this is the scale of conversion efficiency, so it is up to 20, and this is band gap. So these are the higher band gap, and then going to smaller band gap materials. Okay. So if we look at TiO2, this is the first material which was used for PC water splitting, and we have also written the equation when we use TiO2 as a photoelectrode material in our previous class. So if you look at TiO2, this is a position of CBM and this is a position of VBM, and these are the lines. This is HER and this is OER. Okay. So it seems that the TiO2 is nicely positioned as compared to, or the TiO2 band edges it's a nice position as when we compare it with HER and OER lines. Okay. But the efficiency is quite low. You can see the efficiency is only, even it is just 2%, 2 to 2.5% around. So the reason is that as its band gap is quite large, the lot of photons gets transmitted. That is what I mentioned. So absorption probability of light inside TiO2 is less, although it is having better stability. So that's why people started thinking that let us go for other oxide materials also. Okay, some potential oxide material which people have used for many other technology, and some of the materials which they have used, one is WO3. So if you look at WO3, WO3 is also its CBM and VBM are position. Okay, fine, because this should be slightly higher, but it is okay. It is almost touching the HER line conduction band minima, and there is an enhancement in the efficiency. So when you use WO3, okay, you have almost about 6% efficiency, and this band gap is slightly less as compared to TiO2. So this is a typical band gap of TiO2 and this is a band gap of WO3. So you reduce the band gap, that means you start, the absorption of light efficiently inside the photoelectrode, and therefore you have higher efficiency. So accordingly, if we go, BiVO4 is a material which is being studied recently, and people find lot of potential in BiVO4, and with this also the CBM and VBM are positioned nicely. Its band gap is slightly smaller as compared to TiO2 and WO3, and it is giving an efficiency almost 8 to 8.5%. Okay, but maximum efficiency one can obtain in Fe2O3. So you can see its band gap is around 1.8 to 2 electron volt, very close to 2 electron volt, and although its conduction band minima is slightly below as compared to HER line, but it gives very high efficiency. Okay. So, when we just look at the efficiency versus the band gap, these actually these criteria, it makes Fe2O3 as a good material or the best material, best electrode material for PEC water splitting. However, there are various other aspects which we will discuss later when we discuss case studies, and we will see that what are the the best material that one can choose at this moment as electrode material for PEC water splitting system. Okay. So, now let me make a comparative chart of various materials. So, you can see this these are the system, this PEC tandem system, PEC PV system. So, I have not discussed so far about the systems. We will discuss about the system in the next classes, but let us just think about that there are some PEC tandem system exist, PEC photovoltaic system exist, and now our main idea is to look at how the efficiency and other properties varies when we consider different material. Okay. So, this is a 3,5 material, okay, and then this is a typical photocurrent density, and also you have to check the durability. So, you can see the durability is 8 hours, and this is a typical electrode area when you make it in a PEC water splitting system. So, you can have the heterostructure with WVIVO4, and then you have current density slightly lower with efficiency also slightly lower, and durability is slightly less, and electrode area is slightly higher. One can see that with high the area of 50 centimeters square, what is the efficiency that one can talk about, and if you use Fe2O3 as a photoelectrode, you do not have very high efficiency, around 0.6%. Okay. However, you have very good durability in this case, so you can use it for a long time, and ViVo4 can be used as an electrode material and can be having a durability of 7 hours here, okay, in different solution that is being used for photocurrent generation or as an electrolyte. So, another typical example of higher efficiency is again 3,5 material, which is 19.3% efficiency with a durability of 20 hours, and this is an efficiency where we take a slightly different counter electrode. We generally take platinum, but one can have a silicon, titanium, platinum or tri-layer, and one can have efficiency of 17.6% in a small PEC cell. So, this entire table gives us an idea about how one can choose the electrode material and what kind of efficiency one can see. So, we have lot of literature existing now in PEC water splitting system. So, one can look at into the literature and find different efficiency of different material. Okay. So, it means there is a good amount of variation of PEC or water splitting efficiency when we consider different material. Okay. So, now the important point is that when I use suppose an oxide material as a photoelectrode, let us consider again back to TiO2. Okay. This is a very conventional material, people are using TiO2 still today. But as we have seen that when we use TiO2, we do not have very high efficiency. Okay, the efficiency is small. The reason is that the TiO2 is having large band gap, okay, and bandage positions are not very favorable. So, you can see this is hydrogen evolution reaction, this is oxygen evolution reaction, and this is a typical band gap of N-type TiO2. So, this is valence band maxima and this is conduction band minima. So, if you look at the absorption of light in TiO2, so you just see that this is the solar spectrum where this is 5% UV, this is 43% visible, 52% is infrared. So, because of very large band gap of TiO2, we miss lot of portion of visible light in TiO2. Okay, only the photons which are having higher energy gets absorbed in TiO2. So TiO2 as a material, although has different good properties as an electrode or the potential material as electrode, but if I just think about a pure TiO2 as a photoelectrode, then it seems that it is not that promising as far as the efficiency is concerned. So now the question is the engineering of material. Okay. So in my previous modules also, when we discussed photovoltaics and when we discussed thermoelectric generator, we always talked about engineering of material. Okay, that means one is to design the material in such a way, or one is to change the properties of the material in such a way that one can have a better performance. Okay, so the important point is that because of its large band gap, it seems that TiO2 is not a very efficient material in PEC water splitting system. So what we need to do, we try to the reduce band gap. So it is not possible, you cannot reduce a band gap of a material in pure form. So what one can do, one can dope it with different other element. So one typical dopant in TiO2 is carbon. So what happen if you dope TiO2 with carbon? There are some other materials also people tried, but this is one example which I am showing the initially people have studied is a carbon doping. Okay, and that gives a modification of the band gap of TiO2. Okay, so one can have transition metal doping, one can have nitrogen doping, one can have carbon doping. So you can see there is a carbon doping. So what happened when you dope any material, it actually forms interband states. That means it forms energy states in between conduction band and valence band. Okay, so now earlier the photons which are actually getting transmitted through the band gap, now they have an opportunity to get absorbed because of these intermediate energy states, and that you can see here the absorption enhances, or the low energy photons also get absorbed when we have carbon doping. Okay, so we all know that the absorption process one can study using a simple UV visible spectrometer, where the absorption of light is measured in terms of wavelength, and there is a strong absorption when you consider this and this of the low energy photons when the carbon is doped. And now if we look at the performance of this particular photoelectrode after doping with carbon, then you can see there is a huge rise in the photocurrent density, huge rise. So this is something here, and then we have a huge rise in the photocurrent density after doping of carbon. Okay, so that means this way, if we can you know um, engineer the material or modify the property of the electrode material, we can have a better performance. But one thing which we should always remember, that we would always like to work with a pure material, because more and more defect you generate, this also creates a recombination center. So this aspect I have already discussed in photovoltaics. So if there are different recombination centers in charge carriers, movement gets hindered and there is a recombination process. Okay, so these are the trade-off processes one is to take care when one design a photoelectrode material. So this is one particular process, that means doping could be one important the process by which we can modify the property of the electrode and can have a better performance, as I have just now shown it as an example or as a case study. Another important thing is plasmonic effect. Okay, so in photovoltaics we discussed in detail the plasmonic effect. Let us again try to recollect what we discussed in plasmonic effect. What is plasmon? Plasmon is that when we have particularly the localized surface plasmon, when we have some nanoparticles. Okay, in case of photovoltaics we have seen that when we have nanoparticles on the photovoltaic material, and when light comes there, then there is a kind of the strong absorption by the process of plasmon resonance, localized surface plasmon resonance, or LSPR. And we know how it happens, because if you consider this is a metallic nanoparticle, and there is an free electron cloud. Below that there is a positive ion sheath, and then there is a kind of oscillating motion. Okay, this thing we had already discussed, and because of that there is a strong enhancement in the electromagnetic field very close to the nanoparticle. This leads to a strong absorption. So the same thing one can introduce in PC water splitting also. So what you do, that you decorate or you load your photoelectrode with different metals, okay, particularly those metals which has a strong surface plasmon resonance. Okay, so if you remember, we already discussed the silver, gold, copper. These are the metals which shows lot of promise as in as LSPR, and therefore if we have a sort of decoration of our electrode, so now I have an electrode, okay, photoelectrode, all right, and I decorate this photoelectrode with a different metallic nanoparticle. So this is photoelectrode, and now it is decorated with different nanoparticle, say silver, gold, copper, etc. Okay, we can also little bit dope this particle inside the photoelectrode. So what happens when you have different amount of loading of nanoparticle in the photoelectrode? So this is one particular case study which shows very clearly that how absorbance enhances when we have different nanoparticle of different concentration or grown for different times. So you can see there is a black one which is pristine zinc oxide. Zinc oxide here is used as a photoelectrode material, and then the gold is deposited on zinc oxide for various time, for 30 seconds, 45 seconds, 60 seconds, 75 seconds. That means you load it with different amount of gold nanoparticle, and then you look at the absorbance, how absorbance changes. So you can see that this black one is the pristine, where there is no gold nanoparticle, and it is almost flat, very low absorbance. Then as soon as you start loading it with the gold nanoparticle, so the red one is 30 second, the blue one is 45 second, and the maximum you see in the green one 60 second. Okay, in 75 second also you see good the absorption. So it seems that after 60 second that it is not playing any role in enhancement of absorption, and these things we already discussed in photovoltaics, because one should have an optimum amount of concentration of the nanoparticle to have maximum absorption. Okay, and also the separation of the nanoparticle is also important in order to have a maximum absorption. So in this case it is appearing that the 60-second nanoparticle or gold 60-second time nanoparticle growth of gold, when it was done for 60 seconds, it is seen that it is having maximum absorbance. Okay, so let us see how it is going to impact the results in PC. So if you look at now the photocurrent, and for different cases, so again, so this is the dark one, okay, and then this is a pristine when there is no gold nanoparticle loaded, and then you can see there is a huge enhancement in the photocurrent density. Okay, so again, see the 60-second, as I mentioned, this particular one, it shows the maximum photocurrent density. So that means it is having maximum absorption and it is having maximum photocurrent density. So this is another way one can design the photoelectrode for better efficiency with better absorption of light. Okay, so let me see some more example. So this is another very interesting example of plasmonic effect, where the platinum is coated on TiO2. So the previous example we have seen that carbon is doped in the TiO2. Okay, this was one process. Okay, but we always know that this, whenever we have a lot of doping, then we have some kind of recombination center, and therefore we thought that there should be another process of making a better performance for TiO2, and this is one particular approach. So you load it with platinum, so you can see that TiO2, the black one is the TiO2, and there was no platinum, no particle. And then if you record the absorbance with platinized TiO2, then you can see there is a huge rise in the absorption. Okay, and this simply again this surface plasmon resonance effect, because of SPR there is an enhancement. And then if we try to see how it is going to impact the PEC process, so again when you plot current density versus applied potential, the red one, the black one is only with TiO2, and the red one is TiO2 with platinum, and there is a huge enhancement in the current density when we have TiO2 with platinum. Okay, so one more example which is even more stronger. So in this case, again TiO2 is used, and TiO2 is now coated with copper. So as I told you that copper is also another very good metal for surface plasmon resonance. So in this case, TiO2 is coated with copper. Okay, so or copper nanoparticle, and you can see there is a huge enhancement in hydrogen production. So this is with only TiO2, which is very small. Okay, and we know that why only TiO2 is not very good. And as soon as you put copper, immediately you actually introduce the LSPR effect in that. So when you introduce the LSPR effect, there is a huge enhancement of light absorption, which leads to finally huge enhancement in the hydrogen production. Okay, so this is very significant. Okay, it is almost like zero, and when we talk about millimole per gram of hydrogen production, you can see almost it is going to 40, which is extremely high. Okay, so this means that plasmonic effect is really very good, the effect to, or very nice process to engineer the photoelectric electrode material in order to have a higher efficiency. Okay, so at this stage, if I just want to design my photoanode, okay, so we will discuss the photoelectrode electrochemicals setups in our future classes, but let us see that the first thing is that we have to design the photoanode. So we have to remember three criteria. So it seems that one can have the metal oxide nanotube as a good photoelectrode material. Okay, and we all know that there are several advantages of nanotube. Okay, so what are the advantages of nanotube? So generally in the nanotube, the absorption distance for photons is, it is decoupled from the diffusion length of the propagated charge carriers. All right, this should not be coupled with the diffusion length of the propagated charge carrier. So this is one. And then engineered photocatalyst. So when we talk about engineered photocatalyst, that one engineering I discussed by carbon doping, another engineering we discussed about SPR. Okay, so that means I can have a photocatalyst or photoelectrode in such a way I can have very good enhancement of absorption by loading with nanoparticle, okay, or with the enhancement of SPR. So this is the plasmonic effect, which supplies hot electrons, improves the efficiency, improve hydrogen production. And then there is another criteria, if we can introduce a magnetic nanoparticle also. Okay, I have not yet discussed in detail what is the importance of magnetic nanoparticle, but if we introduce magnetic nanoparticle also, it will make a kind of, the electrode where we can see dissipation less current. Okay, so let me put this also in my criteria of designing a photoelectrode. And finally we can have heterostructure. heterostructure with metal oxide. We can have two different metal oxide, two different semiconductors, okay, and then we can have an electrode with a heterostructure. So what it will do? It will improve the carrier dynamics, carrier generation through large solar spectrum, carrier separation, carrier transport, everything. All right. So this way one can design a metal oxide based photoelectrode. Okay. So we have designed a good photoelectrode, and then let us going to put this photoelectrode in our PC water splitting system. So the next step should be to understand a proper PC water splitting system or PC cell, a single PC cell. Okay. So before we go to the discussion for the PC cells, a single PC cell or tandem PC cell, we have to understand what is the criteria of the characterization, material characterization or efficiency calculation which is needed in order to make a PC cell. So I will just look at this flow chart before we go to the PC cell or the PC technology. So let me start with the first point. So the first point is material design and synthesis. So I have two materials. One is photoelectrode, another is counter electrode. Suppose I fix a counter electrode, suppose I make it only platinum, then what I can vary is the photoelectrode. So I choose a material. Okay, we have so far we have discussed many materials. So let me choose one material. First I will design and fabricate, and with easy synthesis route, let us first make this material and the photoanode or photoelectrode. So what the second thing we have to do, we have to do a UV visible spectroscopy, and then we have to ask that is it strong enough, the absorption is strong enough. If it is yes, then we will go to next step. If it is no, then we have to again design experiment in such a way, we have to follow this path, and then again we have to get a better material. Okay, and then again test the UV visible spectroscopy. If it is yes, then we will do a conductivity measurement. Okay, so if it also good, conductivity measurement is also good, and then then we have to check the current onset. Okay, if this is also yes, then we will do an efficiency measurement. Okay, if it is no, then we have to follow again this path, check the design of material, synthesis of material, coming back with UV visible, and then come out of this loop. So now suppose it is yes, then we have to measure an STH efficiency, as I mentioned, the solar to hydrogen conversion efficiency. If it is yes, okay, so now we have to check the efficiency when it is used as an electrode for a particular radiation, say for AM 1.5. Okay. So this is all right. If it is yes, then we go to this path. We also check the H2O2 production, okay, in the PC cell, and if it is yes, then finally we do a stability test. All right. That means we have to check that for how long one can use this material in PC water splitting system. If it is no, then we have to again check the H2O2 production. If this is again no, we have to come back to this process, if so that this we can go to this path and again go back for the stability test. If everything is no, then we have to again go back to this process and start from the beginning. Okay. So this is a flow chart which is given in the literature, and this is the way that one should start working with a PC cell. So in the next lecture we will discuss how a PC cell is designed, what is the basic structure of a PC cell, and therefore it is extremely important that we remember this particular flow chart, because we have to start from the beginning and go to the designing of a PC cell, single PC cell or tandem PC cell. Okay. So if I just summarize that what we have discussed today, we discussed about the N-type and P-type semiconductor when used as photoelectrode material, how the energy bands bend, and then what is the flow of electron and hole leading to the HER and OER reaction. This is one fundamental point which we discussed, and then we discussed a very important process, all the photophysical process and photoelectrochemical processes involved in PEC, what at the time scale. Okay, so we have also shown the absorption time scale or recombination time scale, transport time scale, and finally the hydrogen oxygen evolution reaction time scale. Okay. Then we have considered one particular class of material, oxide material, as a photoelectrode material. Okay. And then we have seen what are the criteria, what are the important criteria that one needs, and what are the important oxide materials that one need to explore in order to use them as a photoelectrode material. And then the engineering of this oxide material is also important. Two engineering aspects have been discussed. One is doping with carbon, another is use the SPR effect. So SPR effect seems that it is very promising, and that can make a design of our photoanode or photoelectrode which we can use in a PEC cell for hydrogen production. I just mentioned that one can have a very good situation if we have, along with the SPR, if we have a spin system. That means if we load the magnetic nanoparticle also, so that you have a dissipationless current, and then we can design the photoanode. Even we can make a heterostructure of that. And then before going to a PEC cell, single or tandem PEC cell, one needs to know what is the flow chart of characterization and what are the important points in the characterization in order to use this material or the material which has been prepared by research for a technology. Okay, thank you.